Thank you for the introduction. Good morning, everybody. Thank you for attending my virtual presentation. I would also like to take this opportunity to congratulate and thank both the organizing committee and the secretariat and staff who managed to put such a big virtual conference together in a very short period of time. The title of my presentation is a no blade, no rotor current energy converter. It's balanced between current energy conversion in general and the concept that we have developed. Also, there is a PowerPoint presentation that we have uploaded that has more technical details. So anyone who is interested in finding more technical details and graphs that I have left out of this presentation, you're welcome to download that PowerPoint presentation. My presentation has 5 parts: a small introduction about hydrokinetic energy. How much is it and where is it? The challenges that we face to harness this hydrokinetic energy. What is the objective in terms of levelized cost of energy? Then I will talk about the theory behind the concept that we have developed. We have developed a concept that we introduced back in 2006 at the OMAE conference in Hamburg. And there have been a lot of universities and laboratories around the world that have done an excellent research job. There are more than 1,000 papers and publications on the issue of generating hydrokinetic energy using vortex-induced vibrations and galloping. As you know, VIV and galloping are destructive phenomena that we're trying to suppress in offshore engineering. In this case, we're trying to enhance them and control them. And in the process, we found that there is a lot of similarity between the way we convert hydrokinetic energy to useful electrical energy and the way fish propel individually or in schools. The technical section will be talking briefly about the research advances that we have made over the past 10, 15 years. But as I mentioned, there is a PowerPoint presentation that has more details. And then at the end, we will talk about some design consideration, both specific to the concept we're developing and general to hydrokinetic energy conversion. Marine hydrokinetic energy. We get our energy from the sun. The vast majority of it gets either absorbed or reflected. The amount that stays in the oceans, wind, and biomass is only about 10% of the solar energy that reaches Earth. But as you can see, the vast majority of it is absorbed by the ocean. There is a 3% that is being absorbed by wind and is captured by biomass. And even these amounts are much bigger than the world energy consumption. Okay? The other thing to take away from this slide is that the vast majority of the energy absorbed by the oceans is in the form of thermal energy. Thermal energy is a low quality energy and much more difficult to harness it and produce electricity. On the other hand, we have hydrokinetic energy in tides, currents, rivers, and waves, which is a higher quality kind of energy. We can convert it to motion, either an oscillator or in a turbine, and then convert it to electricity. As you know, there's a frantic race to increase the amount of renewable energy that we use. People are optimistic that within 30 to 50 years, we will be able to be on a sustainable energy model. I think this is very optimistic. Energy is the backbone of our civilization. We're going to be using every source of energy that we can put our hands on. And of course, fossil fuels, natural gas, petroleum are not going away anytime soon. But you can see here the progress, there's progress to use more uh, renewable energy, but the change is relatively slow. In a decade, we have a change of about 3%. Hydrokinetic energy, there is vertical in waves and horizontal in tides, currents, and rivers. And we're talking today about horizontal hydrokinetic energy. It is proportional to velocity cube and to the area swept by the devices that we use to harness that energy. It is clean, it's renewable, it's worldwide available. It is easy to forecast it over long periods of time, and it's collocated with existing electrical loads. And because the time variations are not correlated in any way to wind or solar, it is possible to complement other sources of renewable energy using hydrokinetic energy. Also, as we know, at least in the United States, 50% of the population lives within 50 miles from a shoreline. And so the fact that hydrokinetic energy is close to population centers is a bigger incentive to use hydrokinetic energy. It can be, all the devices can be connected either to microgrids in remote areas or large-scale utility grids. The Department of Energy, and particularly the wind and the water power program, have done a terrific job in the past decade trying to evaluate how much energy is there. It's a very difficult task, and they are presenting results in the form of theoretical and practical harnessable energy. You can understand, of course, that this depends on technology, how close this energy is, the source of energy, how far offshore we want to go in order to bring it back in. There are two things we can do in order to increase the practical amount of energy. One is share waters for different usage, navigation, fishing, boating, recreational, and so on. And the other, which is most important, is how do we decrease the onset velocity of operation of converters so that we can expand our ability to harness energy from currents, particularly from slow currents. The incentive, of course, is the blue economy. It's expected to become, to grow to trillions of dollars in the next decade. And there are lots of consumers in that area. Deep sea, oil and gas operations, ocean mining, autonomous vehicles, aquaculture, desalination, you name it, there are lots of reasons to have hydrokinetic energy. The bottom line here is that horizontal marine hydrokinetic energy remains largely untapped because there are many technical challenges. So let's talk about challenges. Under the umbrella of sustainability, we can identify several challenges which translate to design requirements. Then we will discuss how many of those requirements we can satisfy with the concept we have developed. Sustainability means avoiding depletion of natural resources to maintain an ecological balance. In other words, meet the present needs without compromising the needs of future generations. Sustainability has three pillars, the three Ps: planet, profits, people. And those translate to environmental, economic, and social challenges. Environmental, the most important, of course, is that we show respect for the oceans and all the living creatures in the oceans. Economic, it means that we have to achieve a low levelized cost of energy in order to have a competitive technology. Otherwise, any technology would not survive. And of course, we have to appreciate that the people that live near shore are occupying very expensive real estate. They paid a lot of money in order to live in that area. And so we have to share space with them, keep low visibility, and be flexible. We have identified 27 design requirements. Probably the list is by no means exhaustive, but On the other hand, we have probably identified the most important ones in several categories. It's important that we have fish-friendly technology, which means we need to prevent impact either by using sensors and shutting down hydrokinetic turbines, or somehow having blunt surfaces for impact with low speed, because high speeds, like for example what we get in water turbines, 20 to 40 meters per second, and wind turbines, 85 meters per second, those are deadly. And the question is, are there alternatives to big blades? And yes, we have oscillating cylinders, which is the technology we have developed, or oscillating flaps. And there are other requirements like low noise, low electromagnetic emissions, no lubricants, no sediment transport. Social considerations that we have briefly discussed. If you look at this picture here, that's where we deployed our technology. On the other side, you see Canada, here's St. Clair River, and on this side is the United States. And if you look at the aerial picture, this is the point where we operated, and you can see how close we are to shore. This yellow line is the navigation line, which means that most of the river is taken by the big boats that operate in the Great Lakes. And we have to be flexible and have low visibility, basically being able to submerge the hydrokinetic turbine so that we do not have objection from the people in the community. Performance, the two most important ones are, number one, low onset speed. We need to lower the speed at which our hydrokinetic energy devices can operate. The vast majority of currents are slower than 1.5 meters per second. Rivers are typically slower than 1 meter per second. Hydrokinetic turbines need a minimum of 2 meters per second, and preferably 5 to 7 knots, that is 2.5 to 3.5 meters per second, to be financially viable. There are only 7 places in the United States where we have such high speeds. Of course, there are other places in the world, like the British Channel, southwest Korea, where there are high speeds, but basically those places are few. Then we have to design for variable inflow speed. Tidal flows change continuously, river and ocean flows change seasonally. The other important constraint is operating in turbulent flows. There are lots of places where there are turbulent flows. Depending on the size of the turbulence, we may have to design our converters in a different way. Will the turbulence change the angle of attack on blades, or the turbulence hitting cylinders, or the angle of attack on flaps? Then, because of the change of velocity, we need a broad range of high efficiency. Basically reach 80% to 90% of the Betz limit in order to have a viable system. And we have two important metrics. One is a 3-dimensional, the other is a 2-dimensional. The 3-dimensional is power to volume. This is the Achilles heel of all renewable energy technologies. If you look at wind farms at the rated speed of 12 meters per second, we're talking about 1/100th of a watt per cubic meter. 6 orders of magnitude below diesel engines. Hydrokinetic energy is somewhere in between. Then if you prefer to look at a 2-dimensional metric, that would be the area swept by the rotors or the oscillating cylinders over the equivalent mass. If you try to maximize this, of course, you may exceed some limit that will increase the noise. Under durability, you know that we have to operate in harsh environments, which is probably fine. That's what we are designing for. But on the other hand, we have to do the deployment, the retrieval, maintenance, redeployment. These are very difficult operations. Sometimes we may even have to use cofferdams. But we also have to conduct static, dynamic, and fatigue analysis, and same thing for the mooring system. Then if we operate in a river, we have logs. Logs can be heavy, they can destroy really hydrokinetic turbine. So we have to build a shield ahead of a hydrokinetic turbine, and we'll be generating turbulence, which may affect the flow on the oscillating flaps or rotating blades or oscillating cylinders. In design, we have quite a few requirements as well. The most important is that we need somehow to integrate the deployment vessel with the hydrokinetic turbine, because the cost of deployment, retrieval, maintenance is prohibitive. If we use some automation, we will be able to reduce that cost dramatically, and that's a key factor. Then we have several levels of co-design. For example, control co-design. We have moving parts. We want to harness energy. We apply damping on the moving parts in order to take energy out. That may over-suppress motion. So there is a co-design process there, the way there is a co-design for operating expenses, fabrication, and so on. And we have reached the last of the design requirements, which is the most important: achieve a low levelized cost of energy. Again, the water power program of the Department of Energy has done a terrific job processing data and finding the levelized cost of energy of the technologies that they have been supporting for development. There are 3 different scenarios depending on whether we are near a utility scale facility or we're in remote areas, or if we have a riverine system or a tidal system. For each one of those 4 scenarios, they have calculated also the objective levelized cost of energy. The bottom line from this slide is that we need to reduce the levelized cost of energy by 60% in order to have competitive technologies. That's a tall order. Here I just summarize all the design requirements under the 6 categories that we have discussed, but I would like now to reclassify those requirements in terms of those that can be solved with a concept that we have developed, that is the Vivace converter, based on instabilities and fish biomimetics, those that can be solved because of these properties of this concept that we have developed, and finally, a small category of concepts that have to be solved for any concept. And as you can see here, fish friendliness is the top one that we have resolved. No rotors, no blades, low tip speed, and so on. And all those we will discuss after the technical section in this presentation. Let's talk now about the underlying principles of the concept of the Vivace converter. We use instabilities that are catastrophic in offshore engineering and other engineering disciplines. We enhance them, we control them, and we convert hydrokinetic energy to mechanical and subsequently electrical energy. Vortex-induced vibrations, galloping, hard galloping, synergistic flow-induced oscillations of multiple cylinders in groups are these kind of instabilities. And there are lots of similarities between the dynamics and kinematics of groups of cylinders or individual cylinders with fish schools or individual fish in forward motion. There are 4 biomimetic principles that the Vivace converter is using, and the objective is to mimic fish school dynamics without the complexity of fish school kinematics. Let's make a quick comparison between how things move in air and how they move in water. In a steady flow, in air, you typically use a lifting surface and you get a steady lift. Birds coasting, or windmills, or airplanes, or sails of sailboats, that's the way they move. The picture is completely different in water. If you look at a fish in forward motion, it generates, by flexing its body, undulating basically at certain frequency, it generates an alternating wake, which is a drag wake because the fish is putting energy into the flow. On the other hand, if you look at a stationary cylinder in a steady flow, it generates also an alternating wake, but it's a thrust wake because the cylinder puts a resistance against the flow. If we move now to a school of fish, and you observe here the two leading fish, the gray fish, they generate two drag wakes. The black fish in this diamond formation in a fish school moves between two half wakes. And if you combine these two half wakes from the gray fish, then you get a thrust wake, which is similar to what you get from a stationary cylinder in a flow. There has been a 10-year-long study funded by the Department of Energy, which ended several years ago, where fish were put in rivers behind cylinders, stationary cylinders, and they observed the behavior of the fish. The fish relaxed, they spawned more, they thrived in the cylinder wake. Now, let's talk a little bit about vortex-induced vibrations, even though most of you know about it. Whether you call it lock-in or synchronization, or as we proved last year, we have an eigenrelation that the oscillating cylinder has to follow, you are talking about an alternating lift force, alternating wake, and you are talking about a very broad range of synchronization over which the cylinder has large amplitude of oscillation in spite of the change of the inflow velocity. The other thing to remember is that this is a very highly scalable phenomenon. Tiny fishnet filaments or big buildings can go into VIV. And the picture, of course, of kinematics gets even more complex when you have multiple cylinders. How does the response amplitude operator for vortex-induced vibrations look like? It depends on the flow regime and some other properties. If we are in the relatively low Reynolds number regime, on the order of 10,000, then you have the classical figure that we have from about 20 years ago by Williamson, where you have the initial branch, the upper branch, the lower branch, and desynchronization. If you move into high Reynolds numbers between about 20,000 and 300,000, as we have done in my lab, then you are in the so-called TRSL3 flow regime, transition shear layer 3, where the shear layer is fully turbulent and the lift is much higher, 3 to 10 times higher. They have the common characteristics that we have an initial branch, an upper branch, which in this case overtakes the lower branch. You have a minimal lower branch and then desynchronization. The amplitude here goes up to 1.8, 1.9 diameters with a smooth cylinder. The common characteristic, of course, is that you have a broad range of synchronization. This range of synchronization depends on the stiffness and the mass of the oscillator based on the eigenrelation that we derived last year. And when you put this into practice, you have here a smooth cylinder oscillating, connected with a generator, and then it lights bulbs. And this was a video that we developed 15 years ago, and we used it to get funding from the National Science Foundation first, and then the Office of Naval Research, and for the past 7-8 years from the Department of Energy, in order to develop the Vivace converter. The other form of instability is galloping. You can see here in this animation from computational fluid dynamics that we have an alternating wake, alternating vortices, and we have alternating lift that moves the cylinder transversely to the flow. But this is not the driving mechanism. Galloping is an instability. It starts at a certain velocity, the onset velocity, and it keeps increasing in amplitude until the structure breaks down as the velocity increases. It's an instability, and if we didn't have a mechanism to reverse the motion of the cylinder would move in one direction. Even though you have these oscillatory, the oscillatory motion, the alternating vortices, these are not the ones that drive the cylinder. The cylinder has a turbulent stimulation here, which makes it gallop. It moves in this particular experiment plus or minus 4 diameters, and it would move in one direction if the frame was not finite. So you have the alternating lift and the alternating motion, but not due to vortices. Actually, sometimes the alternating vortices help and sometimes hinder the galloping motion. Of course, if you put them back to back, then you see what kind of a response amplitude operator we have. It starts a little bit before the natural frequency of the oscillator in quiescent water. And then you can move galloping, as we will see later, a little bit to lower velocities and have an open-ended response amplitude operator. We have other forms of instabilities, particularly hard galloping. You see in this particular case, we have placed turbulent stimulators on the cylinder. The size of those is the thickness of the boundary layer, and we suppressed fully the flow. But if you move it a little, then you go into supercritical Hopf bifurcation, which is what we call hard galloping. Synergy between cylinders can also lead to different patterns in galloping, and you can have synergy with 4 cylinders, which make basically the Vivace converter look like a reciprocating engine with 4 pistons in this particular case. Okay. Now let's talk about some of the common properties and differences between fish schools and cylinder schools. Alternating lift. Definitely fish, that's the way they move efficiently in water. So do the cylinders extract energy with vortex-induced oscillations or galloping. Fish extract energy from vertical flows, particularly those that are in the rear, not the leading fish in a school. And cylinders do the same thing through vortex-induced vibrations, galloping, or the superposition of the two. Frequency of oscillation, if you look at an array of cylinders, you will see that the patterns that develop look like the undulation modes of fish. Of course, fish self-adjust the frequency, while the frequency of oscillators is adjusted in 2 different ways. One, of course, is the external, depending on stiffness and mass, based on the eigenrelation that we derived last year. And the other one is self-adjustment, because the oscillator in vortex-induced vibrations has to satisfy the eigenrelation. So once you select the frequency of oscillation, then the properties of the oscillator, specifically the added mass in relation to the mass of the body, the oscillating mass of the body, is specified. Cylinders adjust their amplitude of undulation to the speed they are trying to achieve moving forward in water. In cylinders, we use a similar way. We adjust the amplitude by using adaptive damping, which takes some energy out of the body so that we don't have excessive oscillation, not too much, because that would eliminate completely the motion. And we talked already about the response amplitude operator. And another issue which is very important is synergy. In a school of fish, where fish put energy into the relative flow in order to propel themselves, the trailing fish take advantage of the wake. In the case of the cylinders which are trying to extract energy from the flow, the opposite happens. The presence of the rear cylinder enhances the oscillations of the first cylinder to the point that we can double the energy that we get from the first cylinder. The principles of biomimetics, therefore, that we are employing in the development of Vivace are alternating lift, enhancing instabilities by turbulent stimulation that we then control and harness energy, synergistic instabilities of groups of cylinders and wake gain, and adaptive damping using passive control. Again, the objective that we are achieving is mimic the fish school dynamics without the complexity of fish school kinematics. So what can Vivace do? It can harness horizontal hydrokinetic energy. It is simple to build. Usually we build it with 1 to 4 oscillators. It controls natural instabilities, enhances them and controls them, and we harness energy. It is based on 4 fish biomimetic principles, and by concept, it's fish friendly, but by evidence, we have no blades, no rotor, and equally important is that the flow velocity has a relation to the cylinder velocity. In fast flows, the cylinder velocity does not exceed 1.2 times the flow velocity, and in fast flows does not exceed 1.4 times the flow velocity. So the velocity of motion of the body is pretty slow, particularly if you compare it with wind turbines or water turbines. It's a highly scalable device. It can work from Reynolds number of 40 all the way to infinity with turbulent stimulation. We can harness energy from slow flows. The onset velocity that we achieved in the lab was 0.19 meters per second, that is 0.4 knots. It has a much higher power to volume ratio than wind farms by 4 orders of magnitude, but it's still 2 orders of magnitude below diesel engines. The velocity at which we came up with that number of 602 watts per cubic meter is the equivalent of 12 meters per second in air, which is the rating velocity for wind farms. It is compact, and that's very important because it operates like a 3-dimensional converter, and most important, over a broad range of velocities, it can reach efficiency of 88% of the Betz limit. Over the past 15 years, since we introduced the Vivace converter, we have made numerous research advances. I'm not going to go in detail through each one of those. I mentioned the PowerPoint presentation that we have uploaded, and it has lots of information that you may find useful. I will go through just some basic ideas in the next few minutes. If you have any questions, please send me an email. Most important, this problem is very challenging, and like most modern hydrodynamic problems, we need a holistic approach to tackle it. We need different approaches in order to get complementary information. So we conduct experiments in our recirculating channel, which is pretty large. We have numerous oscillators. We typically use 1 to 4 oscillators. Most important, we have developed a controller, which took a long time to develop, which is an unbiased controller, which can emulate any linear or nonlinear oscillator and its parameters. We do not have to change physically springs or dampers in order to do a different kind of experiments. We just put the numbers and the models in the computer. If you do that, be careful not to include in the closed control loop the hydrodynamic force that you would possibly measure. We conduct visualization, broad field of view visualization, because what is very important to us is the relative position of the bodies that oscillate to the vortices and the shear layers. We have identified 9 patterns of relative motion between cylinders. Some of those patterns produce a lot of energy, some do not. Computational fluid dynamics is very helpful, particularly in understanding the interaction between bodies, shear layers, and vortices. Down the hall, 200 feet, we have a good towing tank where we conduct experiments, and about an hour away from Ann Arbor, we have the St. Clair River, and we conduct field tests. Last year, by revealing the eigenrelation at the interface between fluid and structure, we managed to get analytical expression for the forces which are needed in controls. And finally, of course, we're doing extensive signal processing using fast Fourier transform, Hilbert-Hwang transform, empirical mode decomposition. I mentioned to you that we have low motion of the cylinder, and here are the results, even for a soft spring and a low damping. You can see that the ratio of the cylinder velocity to the flow velocity does not exceed 1.4 for slow speeds and 1.2 for high speeds. This is very important, of course, because in case we have some collision with marine life or with people, this is not a deadly velocity. This picture, the sequence of picture down here is from the field test we conducted in 2016. What we want to achieve, and we believe we have achieved it, is mutual benefit. Fish benefit from vortex flows, and we take energy out of the flows. If we achieve indeed mutual benefit, that's ideal symbiosis between fish and an energy machine. We talked about response amplitude operator. We said that we have an open-ended response amplitude operator starting a little bit before the natural frequency in quiescent water, but how do you design a response amplitude operator? By designing properly the turbulent stimulation, location, size, with respect to boundary layer and so on, you can move galloping to lower velocities, and you can increase the response amplitude significantly, but we can never pull it ahead of VIV. We always have the initial branch of VIV, a little bit of the upper branch, and then we get into galloping. We have worked with numerous nonlinear stiffnesses and in order to find a better nonlinear oscillator. They all have some advantages and some drawbacks, and we can combine the best, but the most efficient one was adaptive damping. In what sense? If the cylinder moves too fast, we impose damping, we get more energy out, we reduce a little bit the amplitude. If it is too little oscillation, we don't want to suppress the oscillation, we ease a little bit the damping and the energy harnessing. You see the response for different spacings, for different stiffnesses. You see the response here for different values of stiffness. We start earlier than VIV. We bridge the gap between VIV and galloping that excessive damping can cause. We increase the amount of power that we are harnessing for all three values of stiffness that we have checked. How much? In galloping, we increase the harness power by 51% to 95%. In transition, of course, we increase it by even more. In controls, we need mathematical models. This is the eigenrelation we revealed last year, a very simple one. We managed to decouple basically the amplitude from the frequency of oscillation, and then for a given frequency of oscillation, the added mass, the properties of the oscillator, including the added mass, are fully defined with respect to the mass ratio. This leads to first order expressions for the added mass force, the force in phase with the velocity, and then we can reconstruct the force pretty accurately. The results are in very good agreement with experiments. We're working on second order terms right now, even though they are not so significant. Synergy between cylinders is very complex. Computational fluid dynamics helps us a lot. Again, as I mentioned, the important thing is the timing between vortices, bodies, and shear layers. We have identified 9 patterns. Again, some of those generate power and some do not. Comparison between two cylinders. We have tested various spacings, a very high range of stiffnesses and mass ratios. The summary of all this research is that cylinders in groups behave just like fish in schools. Specifically, you want to go faster, you get them closer, and you use higher stiffness. These are the optimal values for each one of those spacings, just like what fish do. This is the amplification factor. This is the power you would get from one cylinder normalized to one, from 2 cylinders, 3 cylinders, and 4 cylinders. And you can see that there is a range here where we reach, for example, a factor of 6.4 with 4 cylinders. That is a 60% increase. You convert this to efficiency, and over a broad range of velocities, we manage to get between 80 and 90% of the Betz limit. This is the summary of what we have achieved with our Vivace concept and what we are still working on and we can achieve. In design, Vivace presents an additional challenge. It has variable amplitude of oscillation, and therefore it sweeps different area in the fluid depending on the response of the oscillator. Therefore, the efficiency depends on the response and the swept area. As a result, you see here in the efficiency graph, we have 2 local optima, one for VIV and one for galloping. And in the power envelopes or the power response, we have 1 local optimum for power in VIV and 1 in galloping. The local optima in VIV or in galloping between efficiency and power do not coincide. So the maximum local efficiency in VIV is located at the beginning of the upper branch. The maximum power is located at the end of the upper branch. Similarly, in galloping, the local maximum in efficiency is located at the beginning of the fully developed galloping, while the maximum power at the end of the fully developed galloping. Can we reconcile the local optima? Do we want to reconcile the local optima? Because one, of course, is going to give us higher efficiency, the other is going to give us a higher power. Depending on the constraints that you have, you may want one or the other solution. But on the other hand, in general, you may want to try to reconcile those by properly designing, as we have discussed, the turbulent stimulation. The Department of Energy has done a terrific job recommending ways of doing co-design in order to improve the levelized cost of energy, and they have actually provided a spreadsheet in a 2-dimensional space where one dimension is proportional to the power generated, the other one is proportional to the swept area over equivalent mass, and provided isolines for the present state of the art, future targets, and ways of making the isolines for the levelized cost of energy move towards the target of 2030 to achieve, that is, a reduced levelized cost of energy by about 60%. Finally, let's consider some applications. Both VIV and galloping are very scalable phenomena. So you can design a device to harness a small amount of power, like a fraction of a watt, all the way to a megawatt, or you can harness energy from very slow flows to fast flows, and you can power sensors, or you can power communities. You can have a portable device, so you can connect something to a local grid or a utility scale grid. There are lots of different designs that you can do. You can take the oscillators out offshore. You can have a wall in modular form where you can put several of those oscillators, or you can integrate it in with a vessel in order to move it from one location to another. Or probably what would be the most efficient is integrated with offshore wind turbines, because the infrastructure is in place, and you can definitely take advantage of the currents underneath the free surface. I would like to thank you for your attention, thank DOE for their support, and of course, OMAE 2020. I will be happy to answer any questions that you may have, either now or via email later.